Yeah. Hey, how are you? Do you have an idea of how many problems we should expect on the exam? One through 100? Oh, I was wondering what? Go to Discord. Yeah, I downloaded Discord. I just forgot what and type. I'll answer your question. Exclamation point. How many questions? Somebody go to Discord and type exclamation point. How many questions? All of them.
How's everybody's weekend? It's all right.
I was worked to death at work. Heavy stuff all day and liquid day yesterday.
Wow. That's a bummer. Damn. Couple minutes. Come here. Now begins the onslaught of people trying to ram through the Zoom meeting door. I guess, Jesse. Yes. I guess. All right. 12:30. Let's get started. Lord, thank you for bringing us together this afternoon. Thank you for everything that you do for us. And thank you for the weekend that we just had. Pray that you help everybody just focus this week, get everything done that they need to get done, work hard, and just keep plugging. And then we pray. Amen. All right, all right, all right. So, today we're gonna do some things, right? We're gonna do some things. What sorts of things? These things. We're gonna recap last class. We're talking about pneumatic systems and thermal systems, right? If we finish with enough time, whatever time we get left with at the end, you guys can ask questions about anything. Fine. But we'll see how much time we have at the end, right? Okay. What else? Well, I guess we'll just get started then. Let's recap. So, hydraulic systems. Yeah. And that was the focus of last class. What about them? All right, so we started off talking about hydraulic systems and saying that they have elements just like any other system that we've been talking about. And we can make parallels and analogies between all of our systems. So we can say, you know, resistance is like a resistor is like a damper. The capacitance is like a capacitor is like a mass, right? The emergency is like an inductor is like a. And we came up with our elemental equations, right? The first thing we talked about was right? So how do we determine if something is compressible or incompressible? Like what is the delineation, right? And the way that we determine it is if it has a high bulk modulus, it's going to be more stiff, and therefore we will consider it to be incompressible. Incompressible is good, right? Because incompressible means that it can't be compressed, which means that our density doesn't change, right? We have a constant density. And because of that, when we look at conservation of mass, we could change that, right? To conservation of volumetric flow rate, right? Because we can divide out by the density, which is constant, and then we're just left with volume flow rate, which is great, right? Which is great. It's really helpful. And we talked about capacitance. Well, capacitance is just a function of the change in pressure, right? So capacitance is going to be C P dot. Forget the rest of the equation now off the top of my head, which is core form, but it's a function of P dot, right? And so what are we doing, right? We're looking at this and we're saying, well, the mass flow rate is like our Newton's law, our Kirchhoff's law, right? It's the overall physical law that is governing our system. So how do we use that? Well, the sum of our mass flow rate inside of our system, the sum of our volume flow rate inside of our system, anything that's being stored, has to be equal to the sum of whatever's coming in minus the sum of whatever is leaving, right? Again, the example of the bathtub, right? I turn the water on. As long as I have that on at a faster rate than it's draining, I will have water accumulating in my tub at some constant rate, right? These are really just related rate problems from calc, right? That's basically what it is. But all right, so in that sense, right, when we have a constant volume, tank, right? We can determine the capacitance pretty easily, right? We know that it's the area divided by rho g, and that will give us the capacitance. What is capacitance? Capacitance is the measure by which a system can store the energy due to the change in pressure. If we don't have a capacitance, then we don't include a capacitor or capacitance in our equations, right? Typically, m dot CV relates to the capacitance, right? It's m dot CV is equal to P dot. Right? That's the equation, typically, for a constant volume of capacitance, right? What about resistance? How do we deal with resistance? Well, resistance isn't just a function, right? Resistance is a function of flow regime, right? So if we have a laminar flow, we treat resistance differently than if we have a turbulent flow. And if we have an orifice flow, that's a little bit different than either. So what's the deal, right? Well, with a laminar flow, we have something that's nice, smooth, and linear, right? And that's related via our Ohm's law kind of equation, right? Where we've got the change in pressure, delta P, is equal to Q times R, or R times Q, depending on how you want to write it, right? So the resistance times the flow rate, the volume flow rate is equal to the pressure drop, right? Very similar to Ohm's law, the voltage drop is equal to the current times the resistance. Pretty similar. Where do we get this resistance term, right? We get this resistance term from experimental methods for turbulent case, and really for experimental methods for the laminar case as well. Okay? So that's resistance, right? We have our orifice flow. So how do we use these things, right? Well, remember, you can rewrite all these equations in terms of Q, right? And then you just have to figure out, well, is this a Q that's coming into my control volume or Q that is leaving my control volume? And then you have to plug it in the right place in your sum of the masses accumulating is equal to the sum of the mass flow rate in minus the sum of the mass flow rate out. So the key with hydraulic systems is determining by looking at it, what is, so first of all, what is my control volume? What am I interested in analyzing? And secondly, what's coming in, what's leaving, and is there anything staying, right? And if you can figure out those three things, then you should be able to create these equations, right? Now, what about inertance? Because Dr. D, you didn't talk about inertance today. Because we're not going to talk about inertance ever again. We don't ever model it. It's due to the mass flow rate, right? It's due to the mass flow accelerating in a pipe. We're not going to model it. You're going to see today that there's no pneumatic equivalent. There's no thermal equivalent of inertance. We're not going to talk about it again. We're not going to use it in any problem. It's not going to come up. So there's that. If you did have an inertance, what would you do? Well, we have an equation for it, right? What was it? P delta P is equal to LQ dot, something like that. I don't even know it. Never. I should tell you something. What makes a hydraulic system a hydraulic system? The fluid, right? If you're using a liquid, then it's a hydraulic system. As we're going to see today, that's a little bit different than using a gas. However, we did come up with an equation at the end of last class for when we want to use a hydromechanical system, right? Because if we have a system that requires us to, I don't know, move a piston in a cylinder, right? We can't assume that our fluid is incompressible. Because if it's incompressible, the piston's not going to work, right? Incompressible means it can't be compressed. The whole point of the piston is it's gonna compress and expand, right, on some interval, and that's gonna create our mechanical work. And we looked at that and we said, if we use conservation of mass, we can derive how much for a single-sided piston, right, where there's no outflow of fluid. We can determine our equation, and our equation was P dot. I'm not gonna remember that. I'm gonna have to look it up. Good thing I have a master sheet for when I do things. P dot is equal to beta over V naught plus AX times QN minus AX dot, right? That's what we came up with in our problem. And really that AX dot is V dot. And we talked about it, right? Because beta over V, right? We talked about this volume, this idea, right? And I've said before that V dot and Q are synonymous, right? And they are, but in this case, they're really not. Okay, because Q signifies a volumetric flow rate, meaning that there's some volume of fluid that's coming in. Whereas V dot in this case is how much is that volume changing inside of the piston, right? It's a geometrical constraint. And how do we determine the volume inside of our piston, right? Well, we determine that volume by saying, well, it's just the area times how much my piston has moved, right? How much free room I have in there is the area, the cross-sectional area of my piston head, regardless of what the geometry is, times how far it's moved, right? That's going to give us, if it's a cylinder, then it's going to be area of a circle times the height, right? That's going to give us our cylindrical volume. Great, but there's also some initial condition that we started with, right? So that's how we got V naught plus A times X. And if we take the time derivative of that, V naught is constant, it goes away, we're left with AX. And that's how we got V dot is equal to AX. And that kind of goes with hydraulic and hydromechanical systems, and that is the less than 5 minute version of the entire last class. Right, then we get a problem. You guys have any other questions about hydromechanical or hydraulic systems? A lot of these problems are similar to ones we did in class, the ones that you're going to be expected to do on homework and things, right? Where we did one with, you had a tank that was filling, but there's also discharging, right? So you're filling a tank, but there's also going through a valve on the back end. You can have tank filling problems, right? You can chain that into multiple tanks, right? What would you do? Well, the flow into one is the flow out of the other, right? Yeah. You guys have any other questions on hydraulic or hydromechanical systems? Today's going to be very similar. We're going to build on some of those ideas with pneumatic systems, but it's also going to be a little bit different, and it's going to honestly be more focused on thermodynamic type stuff today and anything else. I'll do my best to channel my best Professor Tomford for y'all. I probably won't do it right. All right. Do I care about head loss? I mean, isn't that just a change in pressure? Really? You want to talk about that? Isn't it just a change? Head loss is just how much pressure you're losing right through your system. Just a pressure drop. So yes, but I'm not going to call it that. Here's the things. We just turned in homework 2. We got exam 1 on Thursday and homework 3 on Sunday. Here's the deal with the exam. Let's answer some questions about the exam right now. Just to recap, if you normally don't come to class on Thursdays because you are a Tuesday student, as dictated by LoudCloud, then just take the exam someplace else, right? All I require is that you have your laptop with the exam on it. You can also have your exam sheet up on your screen, right? That's fine. If you have multiple screens, right, you can have one with the exam sheet on it, one with your test. When you open the test, it's going to be like when you open a homework, there'll be a Word doc there. You just pop up and you do the test. Yeah. Outside of that, right, make sure you have a camera on your workspace so I can see what your workspace looks like. Yeah, Sean. Off on the side is fine. I just want to make sure it's clear of anything besides your master sheet and any paper that you're working with. Some people have asked, can you do it on like a tablet? That's fine. I don't have a problem if you don't use paper and you use a tablet to write on. You can do that. I don't care. Yeah, Blake, what was your question? Yes. So the question was, I'm sorry, I have to get used to repeating all questions now. The question was, is that just joining for the exam, just joining the meeting twice? And the answer is yes, you just join it twice. Okay. Yeah, Jake. So a master sheet does not need to be printed out. You can have it up on your computer screen if you want. I'm fine with that. Yeah, what's up? I would prefer that you have the camera from your laptop on you and a second camera pointed at your workspace. If I have to choose, I would prefer, like, if you do not have more than one camera or one, right, pointed at your workspace. Right, pointed at your workspace. Okay. Anything else? Okay. Cool. All right. Well, I did tell you guys last week. All right. Today is the day. Today is the day It is Harrison's birthday today. He is 5. All right. So for our participation, we will all be singing happy birthday to Harrison. Includes you guys at home. You can see he's got his branch shirt on. He's a big Trolls guy. So all right. So and a 1 and a 2 and a 3. Happy
Birthday to you. Happy birthday to you. Happy birthday, dear Hannah. Happy birthday to you.
All right. That was probably just on par with the other class that did it too. So thank you guys. Appreciate that. All right. He's gonna love that. He really will. All right. So here's other stuff that's important. We got a shake up from last week's activities. Now we've got those numbers on the side are not correct. I didn't update those because reasons. So don't worry about the numbers on the side. Just worry about the numbers on the right-hand side, not the left-hand side. Dr. G sanitizers and the life livers within a point of each other, followed by SDCK, who's running the pack. Static waffles and yikes right there. Everybody's really, really close still. In the bag, 185.31. Zoom engineers, Wizard Lizards, Zero Division, Michael Scott Paper Company, Matilda's Pointy Compass, Doctors Without Doctorates, Warzone, Swarm Lords, and Blank. Okay, so this week for points, what are we doing? Right? It's a great question. It's all tied to exam performance of your team. So your teams, right? The way it's going to work is I will take your teams, I will average your scores together. That will be your representative score. And then you will get placed among the other teams in this class, right? Top 6, there's only 6 teams. So you get points for 1st through 6th place. It'd be like 8, 6, 4, 3, 2, 1, like the typical scoring that we do. Okay. Remember, your other half of your participation points is actually just showing up to take the exam, right? So probably a good idea. I should probably just do that. I would highly recommend. Okay. Cool. You guys have anything else you want to talk about before we jump into pneumatic systems, or you just like you're all so hyped up you can't wait and just want to get going? Right? Yeah, it's that one. All right, let's go with that one. It's fun. All right. So, what is a pneumatic system? Right? Why should we? Pneumatic systems involve compressible fluids, basically gases, right? The way that we defined it last class was that a pneumatic system uses a gas as the working fluid, right? Which makes it inherently compressible. Now, is that always the case? Are gases always compressible? Well, if you guys remember back to thermodynamics, you should have had to at least one time in the whole semester calculate the compressibility factor of a substance, right? And so they can be compressible, but we'll talk about that in a second, right? When we analyze pneumatic systems, we're analyzing complex systems because it's not just the fluid effects of the gases that we have to take into account, but also the thermodynamic interactions that we have, right? We probably all recall that temperature, pressure, and volume are all intertwined with one another, right? And so that helps to complicate things. Compressibility effects may cause oscillations in our system response, right? So it's weird, but sometimes if you compress a gas too fast, it'll fight you, right? And so it'll push back, so you get this little oscillation, right? Flow can become choked at a throat, right? So if you have an orifice plate that you're running something through, you can choke your flow, which means that it would run at sonic conditions, right? So Mach 1. And something being choked versus unchoked gives you a nonlinear relationship that you end up dealing with. For compressible fluids, our mass flow, right, which the book incorrectly uses as W, you guys can, you know, I'm going to send an email to Craig A. Kluver and let him know that he's wrong on this one because it's definitely wrong. W is not mass flow rate. M dot is mass flow rate. So remember, whenever you see a W in the textbook, just turn it upside down and put a dot over it, and you'll be fine. All right. So we have mass flow rate and volume flow rate, right? But remember what happens. Because we're no longer incompressible, because these are all compressible, our density is not constant. And if our density isn't constant, we cannot make the assertion that mass flow rate and volume flow rate are equivalent, right? Because the way that we got there was by dividing out the density. And we can't do that anymore. So because of that, mass flow rate now takes this format, right? So you have to do the entire derivative out. And if you do, you get that equation, right? M dot is equal to rho dot V plus rho V dot. Okay. So there's an extra term that we have to deal with, right? There's an extra term that we have to deal with. We're going to have to figure out what is rho dot and how do we write this in terms of something that is actually palatable for us in terms of an analysis, right? Because it's all well and good, but I don't know how to measure the change in something's density accurately over time, right? But we're going to talk about how we can normalize this based off of pressure from other relationships that we have. So we'll talk about that again in a little bit. All right, so again, right, just like hydraulic systems, we're dealing with conservation of mass, right? So the sum of my mass flow accumulating inside of my system is equal to the sum of my mass flow in minus the sum of my mass flow out. That is our overarching physical law for this, right? So, said it before, but we're going to have to include thermodynamic effects here, right? And thermo is a great class. Everybody loves thermo, right? Because whenever you ask Professor Thompson or Dr. Williams, like, can I have an equation sheet for the exam? They look at you and they say, well, there's only one equation, it's confirmation energy. Right? And then they walk away. Right? Because it's true. It's a class built around one equation. Right? So anyway, pneumatic systems exhibit a functional relationship between pressure, density, and temperature. Looks like this. P is equal to rho RT. Right? P is equal to rho RT. What is this? What is this equation? You've all seen this before. Yes, the ideal gas law, albeit it's written in terms of density instead of mass and volume, right? But same difference, right? Same difference. What R is that? Is that the universal one or is that the gas specific R? Gas specific, right? Because it doesn't have the little u. Doesn't have the little u. Also, it's on mass basis, right? Which is the big clue, because if you use universal, you have to be on a molar basis, right? Which, as engineers, is as mechanical and biomedical engineers, serves no purpose for us whatsoever. All right, so PV is MRT, right? R is the gas constant, T is in Kelvin. Remember, whenever we are talking about things in thermodynamics, we're using absolute temperature scales, right? And if you didn't remember, how could you remember? Well, you look at the units of R, right? R is going to be in Kelvin units, right? Okay. So far, so good, right? So we've got the ideal gas law, and that's going to come back and help us in a little bit. Not obviously apparent, right? But this is how we're going to get pressure in terms of density, right? Or rather, our density in terms of our pressure, right? Because I told you before, we need to figure out what rho dot is actually in terms of something useful to us. And this is the road. This is the road there, the ideal gas law. So just like any other system, we have to talk about a resistance. When do we have a resistance element? The same places that we have them for hydraulic systems, right? Specifically when we have a valve or an orifice, right? Now, in very rare cases, a flow of a pneumatic system can be considered incompressible, but this is going to be something that is an extremely low speed flow. If we have a low speed flow, we can use these nice equations to deal with our resistance elements across our valves. And so we have m dot is equal to delta P over R sub L. Notice that looks a lot like our last one for hydraulic systems. Instead of being in terms of Q, it's in terms of m dot. Same deal for our turbulent. So essentially, if this is an incompressible pneumatic system, we can treat it like an incompressible hydraulic system, right? It's the same operation, right? We have this, it's just that things are in terms of mass flow rate instead of Q dot. And notice we're writing all of our equations in terms of m dot, and there's a reason for that, right? And the reason is that we need everything in terms of a mass flow rate, right? All of our equations from here on out, the pneumatic systems are going to be m dot equals this, m dot equals that. The reason behind it is because conservation of mass is our overall goal, right? It's our overarching law. And if we have to plug all these things into the m dot CV is equal to m dot in minus m dot out equation, our job is going to be to discern what is my mass flow rate in, what is my mass flow rate out, and what is being accumulated by the. Okay, so that is resistance for low speed compressible pneumatic systems, but as it says here, that is rare and likely not going to be the case, right? So how do we talk about systems that we will actually see? So when we have something that's compressible, it's turbulent, complex, so we need to consider choked versus unchoked flow at the minimum area or at the throat. So you look at our picture down there, right? Remember, that's just m dot. And we look at our picture down there, and we've got some upstream pressure, some downstream pressure. Our m dot is moving from left to right. If we know that our m dot's moving from left to right, what can we assume about our pressures P1 and P2? Yep, right. So P1 is greater than P2. Also, it's written there, right? But there's a reason, right? Remember, the pressure gradient drives our fluid flow, right? You have a larger pressure on one side, that is going to push, and you're going to lose pressure as you go across the throat, the orifice, right? So for unchoked flow, our mass flow rate is a function of P1, P2, the area of the throat, and temperature. Which temperature? The upstream temperature. That's a lot of things. So how do we, I mean, that's not just like the function of the change in pressure, right? That's quite a bit. This is going to be complicated, right? So how do we go about doing this? Well, we're going to use these equations. And they're gross. I know they're gross. But these are the ones we're going to use. So the mass flow rate, so the top one is for not choked flow, or some people call it unchoked flow, right? The top one is for unchoked flow, and the bottom one is for choked flow. There's a couple of things that we need to talk about here, right? First of all, C sub D, what is that? That's my drag coefficient, right? Or discharge coefficient, whatever you want to call it. It's essentially a measure of how much friction we have in our system. The area, right? The area of the throat times the upstream pressure. What's gamma here, right? I'm not going to read this whole thing out, but what's gamma? Gamma is the ratio of specific heat. What is the ratio of specific heats? Well, it's the ratio of my constant pressure specific heat to my constant volume specific heat. These are tabulated for us in thermo textbook, right? I believe it's table A1 or A2 in a thermo book, which you all obviously have access to still, right? No. So where would you find this? I think I brought this up earlier. There's this new thing. It's called Google, and you can type it in and find it. If you need one for like an exam or something, good question. If we provided with one, or at least a table where you can find one. But here's my counter question to your question. How many problems have you done thus far where you needed to put any numbers in?
None.
Thank you, Jeremy. All right, so we've got gamma there, right? Ratio of specific heat for air, that's 1 point. Also, we've got our critical pressure ratio, right? And that's defined as 2 over gamma plus 1 all to the gamma over gamma minus 1, right? Which for air is roughly 0.528. What do we do with that? Well, you'll see on the right-hand side here, next to these equations, the ratio of your pressures, if it is greater than the critical pressure ratio, right, then you have unchoked flow. If it's less than or equal to that pressure, okay, then you have choked flow. Yeah, John. Choke flow refers to if you go through an orifice plate or a throat, that you are getting sonic flow coming out from Mach 1 or higher. So it has to do with the speed that you have coming out. So unchoked is less than sonic, is a subsonic flow. So you could potentially go through this throat here, right, and not have a choke flow. You could potentially. So problems, just like we did laminar and turbulent, this is the laminar and turbulent of pneumatic systems, right? This is the laminar and turbulent of pneumatic systems. We're going to talk about it a little bit more in a second, right? And the relationship between these pressures, if they change, what does it look like? How does that affect everything? How does the critical pressure change? How does the pressure ratio changing affect how our flows look? Okay. Oh, everybody. Okay. This is definitely on the master sheet. I definitely put that one on there. Remember, it probably took the longest out of anything that I had to put on. This is the pain in the butt. Okay. So this is great, right? This is good. But what does it mean? The numbers, Mason, what do they mean? Indeed. All right, so we've got mass flow rate for pneumatic systems here, right? So imagine that I have all these numbers are correct, right? Like I provided you with these numbers. We're going to run our example, right? So I've got an upstream input pressure that I'm varying while the downstream pressure is held constant at atmosphere, right? So I've got some pipe, it's got an orifice, it's got a throat in it, and it's on one side is open to atmosphere, on the other side I'm able to change the pressure coming in, right? How does changing that pressure, that input pressure, affect my mass flow rate, right? So we can see here, right, as I increase the pressure is on the x-axis, as I increase the pressure, my mass flow rate goes up. And at a certain point, which happens to be my critical pressure, P1 is equal to 1.92 times 10 to the fifth Newton per meter squared, or, you know, some people like to call it Pascal, right? Well, at that point, it starts to look linear. So your input pressure actually starts to linear relationship as it increases. So when we have choked flow, our input pressure will look linear as opposed to what it looks like in our unchoked flow, right? Which is nice. Right? That's nice. We like things that are linear. We like things that are linear. Okay. So now what? So what if we flip this around and we hold the pressure at the input constant, and we're going to change our output pressure, and we're going to increase it from atmospheric until we get to P1, right? So from atmospheric until we have no flow, right? Because if there's no pressure gradient, we don't have no. What if we do that? Sure, let's do that. Sorry, from vacuum, not from atmosphere. So essentially, we're going to plot pressure ratio on the X and mass flow rate on the Y. And in this case, is that we have a nice linear region where our mass flow rate is basically constant until we hit our pressure ratio, right? Until we get larger than our critical pressure. And then we become unchoked and we lose mass flow rate. So that's nice. Right? That's nice that we know that. How do we use this, right? And this is our resistance equation, right? So if we have an orifice plate or a valve or whatever else we can have, that typically actually it's an orifice plate or a throat, right? A throat's just an orifice. In your line, then you use our equations that we came up with. You plug these in for your M dot. They'll either be in or out, right? Depending on where our control line is. Depending on what's happening in our system. Is it always appropriate to apply these? No, you don't always have to. Remember, we have things for low speed flows too, right? Where the low speed flow will tell us that we can have either laminar or turbulent, right? So if you have something that's low speed, don't do this. Right? It's not appropriate to use this on a low speed flow, but if we have something where you're expressly told that it's compressible, this is where we need to be. Do you guys have any questions on resistance? For compressibles, for a compressible flow, yeah. If you have something that's incompressible, valves, I mean, valves and things still have an effect, right? And you can typically model a valve as an orifice, right, or throat, but you need to know, how far, how much it is open, right? What is the area in there? All right, so let's talk about capacitance. Right? We have pneumatic capacitance. So we talked about this a little bit, right? We can define capacitance as the change dm over dp, right? The change in the derivative of mass with respect to pressure. But we know that the mass is just the density times the volume. So we'll plug that in, right? And we'll massage the equation a little bit. And we can find that dm is equal to d rho v, which is equal to v times dp. So we can rewrite our capacitance as our volume times our change in density divided by the change in pressure. That looks a lot like something that we talked about with hydraulic systems, doesn't it? Doesn't that look a lot like how we defined bulk modulus? Very similar. Zero. But anyway, keep going, right? Both concepts doesn't play here, but what does play is another thermodynamic concept. Essentially, we need to apply a polytropic expansion to this. What is a polytropic expansion? Great question. Tells us that P over rho to the n is equal to A, or I can rewrite that as P is equal to A times rho to the n. What does that mean? Well, what is n? N is an experimental constant that refers to the type of process that we have. So if n is equal to 1, we have an isothermal process. If n is equal to gamma, then we have an adiabatic process, right? There's many more. We can look them up and they're all tabulated. What is special about an isothermal process? What makes it isothermal? What does iso mean? Constant. What does thermal mean? There you go. Constant temperature. It's a constant temperature process, right? What about adiabatic? What's an adiabatic process? What does that mean?
No change in pressure, right?
No, that's
Oh.
isothermal.
Ah, right. Entropy? No change in entropy?
That's isentropic.
Oh my gosh, I'm all over the place.
Isothermal means there's no change in temperature. What's adiabatic? You're getting there, Connor. You're on the. No. Connor's closer with energy. What are the types of energy? It's a specific type of energy, but there's none of it. Yes, no heat transfer. That's what it is. Adiabatic, no heat transfer. All right. I'm afraid I'm gonna have to talk to Comfort about that one, guys. All right, anyway. So we're gonna take what we know about the polytropic process and we're gonna do some math. Okay. Specifically, we're gonna take the differential of both sides. All right, so remember it was P is equal to A n rho to the n. Right, I'm sorry. P was equal to A times rho to the n. That is the equation we started with. Right, and we're going to take the differential of each side. And if I do that, I'll get dP is equal to A n rho to the n minus 1 d rho. Then I'm going to algebra, so I get d rho dP. Why do I want d rho dP? Because that's what's in my capacitance equation, right? So I need to have that. I'm trying to get rid of d rho dP, right? Because again, remember, as engineers, right, and this is good practice as modeling, for modeling and model making, and when we get into analytics of our models, right? We need to be able to measure something, right? If you're going to create a control system, right? If you're going to be controlling something using feedback, you need a measurement to come out of that, right? How do you reliably measure the change in density as a function of pressure? Wouldn't it be easier to just measure the volume, the temperature as a function of the ideal gas constant and whatever polytropic process exponent you have? So I'm rewriting this, right? I rewrite this, I algebra it, right? I get down to rho, I go to the negative n over A times n. Well, if I substitute in A, right, where A is equal to P times rho to the negative n, I end up in this equation, which is d rho dP is equal to 1 over n RT. And remember, this is where it gets confusing because we really want n to be the number of moles, and it is not the number of moles. It's my polytropic expansion exponent. That's 1 for isothermal, gamma for adiabatic. And I can plug that back in to C is equal to V d rho dP. And I get the nice equation down there for when we have a fixed volume. when we have a fixed volume. C is equal to V over N RT, right? So that's how we determine our capacitance if we have a fixed volume tank, which, as I said in this morning's class, is like 99.9% of all tanks that exist. I'm not going to say it's 100%, because as soon as I say that, one of you will show me the Google search where you found this tank that is not a constant volume, right? And I'm not interested in playing that game. Not interested. But anyway, this is how we determine what the capacitance is. It's a function of the volume. Because it's a gas, it depends, right? It depends on how much energy this gas is absorbing, right? That's what the thermodynamic process is telling you, right? Thermodynamics is a class that is all about the transfer of energy. How does that energy change form? And it's telling you what kind of process it is. And it's telling you, is this constant pressure? Is this constant temperature? Is this no heat transfer, right? Yeah, Connie. Yeah. Yeah. And the question was, would a fixed volume tank be something like a propane tank? And the answer is yes. Right? Any compressed gas tank that I've ever seen is a constant volume. Yeah. My brain, I don't think my brain understands what it would mean to be a changing volume tank, because I'm only three-dimensional, so I don't maybe if I had more dimensions, then I'd probably be able to see it, but I don't. I'm working on it though. I'm working on it. All right. Cool. You guys have any questions on capacitance? When do we have a capacitance? When we have a tank. What if you don't have a tank? Well, it's going to be really hard for you to control where your gas is if you don't have a tank. Just saying. Right, just saying. Most gases are stored in tanks. They're really hard to clear out. Right, so. What about a balloon?
Sure, it has like a back. It can be described.
Are you filling the balloon, or is it already filled, or is it empty?
Filled.
Yeah. So then you're basically a tank. It has a capacitance. Right? There's some energy that you're storing in that balloon due to the pressure difference that you've created because there's no outlet. Now, some balloons, not all balloons are created equal. Some are better than others. Right? When you go to, I just did this actually, when you go to Party City and they ask you, do you want to put in the stuff that makes the balloons last longer? What is it, right? It's a gel coating that goes in the balloon so that it actually helps to seal some of the microscopic pores that are in the balloon itself, right? It doesn't do it completely, but it extends the life of the balloon by a small amount. All right, so how do we model a pneumatic system, right? How do we do it? Well, we said before, we've got to use mass flow rate. We're going to use conservation of mass. And if we break it down, we say that the amount of mass that we're accumulating is actually rho dot V plus rho times V dot, right? That's the time rate of mass change in our control line. Remember, these are, again, thermal, fluid, heat transfer. Control volumes are what are important, right? We need to identify, the first thing we're doing is we're identifying what our system is and what is of interest to us, right? The second thing that we're doing is we're applying conservation of mass. Now we're going to use our polytropic process here again. Why? Because of this term. Because of rho dot. Rho dot is great, right? I understand that the density is going to change as a function of time. I get that. I don't know how to measure that. What I do know how to measure reliably is pressure, right? It's very easy to measure the pressure inside of a tank. We have tons of devices to do that. It's not so easy to measure how the density changes as a function of time without being invasive to the tank, right? Sure, we could do it. So how do we do that? Well, we're going to rewrite this equation, right? Or polytropic process. This time, instead of taking the differential of both sides, we're taking the time derivative. So we get P dot is equal to A and rho n minus 1, rho to the n minus 1 rho dot. And we can move things around. And we end up with this equation where I've circled that in red. What is that thing in red? That's just A times rho to the n, which is equal to pressure. Right? That comes from what? That comes from our actual polytropic process equation. So I can plug that in, and I'm left with rho dot is equal to rho divided by n times p times p dot. And now that's nice, because now I have rho dot in terms of the pressure. The pressure is more interesting. Right? More interesting. We're filling a tank, right? You need to know how fast the pressure is changing and what the total pressure is. You don't want to overfill the tank, right? If you overfill the balloon, bad things happen. Right? They pop, kid starts to cry, snaps back, hits you in the face. We've all been there. We've all been there. Also, if you overfill the balloon, you can't tie it. Literally, we will cut your finger off. Try to put your finger off. Any questions on it? So what do we do? What's the point? Well, now I have an equation for P dot, right? I'm going to plug that back in. And I've got my conservation of mass. Remember, W is M dot. So M dot inside of my control volume, the amount of mass that I'm accumulating inside of my control volume is equal to V divided by nRT P dot. Right? Remember, that's C, right? This was, we just came up with this. This was C. That's CP dot. Plus P over RT D dot. Which we also came up with. So it's rho dot V plus rho V dot. And that's equal to my net mass flow rate, right? The sum of my mass flow rate in minus the sum of my mass flow rate. Yeah. So it's an M dot. I should, at some point, I should go back to these slides and change it, but I grabbed this one from the textbook, and I figured it'd be better to have you guys know that that's what happens in the textbook in case, you know, for some reason you ever want to read the textbook, which I understand is high on everybody's priority list, for sure. Especially if you can't sleep. No.
So that rho dot V and rho V dot is talking about bottom part of the graph, right? That C is the entire graph.
So let's put it this way, right? So this is saying that this entire thing represents rho dot V. And this entire thing represents rho V dot, right? Remember, we changed rho dot into a function of pressure, right? Now, the other thing that we did a couple of slides ago, and I'll go back and
Yeah, I remember the C part.
C is equal, right? So this coefficient here, right here, is actually C, which, right, which, if we think about this, right, for a hydraulic system, we had CP dot was equal to M dot CV, right? For a hydraulic system. CP dot was equal to M dot CV, or QCV, right? That was for incompressible, right? Something that was incompressible. For a compressible, or something that's compressible, a compressible fluid, we have the incompressible portion plus some extra, right? We have the compressible portion plus a little bit more. Okay. So there's that, right? So what's this red box down here? Well, what happens? We have something similar to last class where we want to, I don't know, talk about like a piston, cylinder, right? A pneumatic mechanical system. Which I mean, we would never have engines and guns, ever. Where gas is driving a mechanical output. This is something that I know it never happened, but just in case it did happen, right? Well, remember, in the piston cylinder, right, we've got this equation. And that's going to be for anything that has a volume that is not fixed, a volume that is changing over time. And so we have P dot is equal to nRT over V. Hey, that's just 1 over my capacity, right? Times M dot net. Remember, M dot net is what? Well, it's M dot in minus M dot out minus P over RT V dot. So just essentially solve this equation that we had up there for P dot. Right? That's all I've done. And we'll call this M dot. Call that M dot. And again, when we have a fixed volume, just get Cp dot is equal to W net. Why? Because if you have a fixed volume, it's not changing with time. So the derivative goes to 0. So that whole term on the right-hand side gets out of there. Right? Gets out of there. Yeah. So for a fixed volume, right, we have this. Fixed volume means that that's 0. The derivative of something that's constant is 0. Yeah. All right. You have any questions so far on this? Everybody doing okay? Okay. It's okay to have questions. It's okay to not be okay. It's not okay to not ask questions. There's a lot of okays in that sentence.
I just need an example.
No, Trevor, I refuse. Fine. Good example. All right, so what do I have here? Right. I've got air at temperature T that passes through a valve into a rigid cylinder of volume V, as shown in the figure 7.5.1. The mass flow rate through the valve depends on the pressure difference, delta P, is equal to P in minus P, and is given by an experimentally derived function, is F of delta P. We want to develop a dynamic model of the gauge pressure P in the container as a function of the input pressure P sub I, assuming that our filling process is isothermal. If it's isothermal, what does that mean for our, what does that mean? N is equal to 1. It is. All right, so what's the first thing we need, right? The first thing we need here, is a diagram. So I'm going to draw this pretty much exactly the way it was just drawn, except with the lines not being straight. So I've got some pressure and some volume in here. I'm starting with this internal pressure here. I've got some temperature out here. I've got some atmospheric pressure there. We were told that this is R sub V. All right. Also told that this is Q. And they call this QMI. I'm going to call it M dot I. Let's write that so that it actually is M dot I. My mass flow rate in. We need to draw a control volume. I'm going to use this tank. Now, what were we told about QMI? Right? The QMI is equal to a function of delta P. Now, we don't know. It's experimentally derived, but they didn't give it. We also weren't told if this was a high speed, low speed, whatever flow, right? That seems problematic as well. Huh. We'll talk about that in a second. What's my input and what's my output? What was that? Sorry, I can't hear. Okay. So yes and no. Yes and no. If we're looking at this control volume, what are we putting into this control volume that we've drawn?
M dot.
Temperature?
M dot I. It's the mass flow rate in. So you're not wrong, Olivia. It all depends on how much of the system that we have in our control volume specifically. Because we do have PN, but PN is really the input to that valve, right? When we're saying that, we kind of already know what the valve has in store for us, right? Because we know that there's M dot I, and we know that that is given to us by some experimental function, right? So we actually don't have to chain everything together. So in is M dot I. What's my output then? What's my output? It is. It is going to be pressure. Why? Because I put some flow rate in and I pressurized the tank. And that's the whole deal. Right? This is a whole class of problems, like tank filling problems, right? You could have another tank that is connected through a valve, like two tanks connected through a valve, right? You could have two tanks that are connected through a valve filling a third tank, right? Like tank filling problems always take the same type of role here, the same method. Whereas you're going to look at the Q in, the Q out, right? You're going to look at the flow rates, the mass flow rate in and the mass flow rates out of your control volume. So what if you had a valve here, right? Well, we do, but what if we weren't told that it's experimentally derived flow rate to the valve? How would we figure that out? We would have to use our choked and unchoked flow mass flow rate equations, which I'm really happy that we don't have to, because writing them is a real pain in the butt. Full stop. Those are long equations. It takes me like a whole slide to write just one of them. And yeah, so we're not going to do it. All right, so what are my mathematical truths here? Well, remember, I've got M dot in minus M dot out is equal to M dot CV, right? Conservation of mass. Question, what is my mass flow rate out? 0. Right. I. Mass flow rate in. So we know, because there's no outlet, right? Because hopefully there's no hole in our tank, right? We're just gonna have M dot in is equal to M dot CV. Right? So the more mass I put in, the more mass is accumulating because it's not going anywhere. It's not going anywhere. What else do I know? Well, This is a constant volume tank or variable volume tank? Constant volume. So what does that mean about my m.cv? Yep. Yep. Is equal to CP dot. Okay. Well, that's fun, right? We also know that C is equal to V over nRT. Right? We derived that. But in this case, it's isothermal, right? So this is really V over RT because, as we said at the beginning of the problem, N is 1 for an isothermal expansion. Okay. And that's really all we need to get this started for our reduction. Yeah, Sean.
When we're doing this on the home test, when we put like C equals B and I think we just take away the N, we want to write down N.
You know, we should write it down. We should. 100%.
Same like the M dot C dot.
I think that one speaks for itself. It's just that you need to have the N is equal to 1 somewhere on there, right? Okay. All right. So we can do our reduction. Where do we start our reduction here? Well, we start with that m dot I is equal to m dot CV, right? Number m dot I is equal to m dot CV. Well, that's just going to tell me that m dot I is equal to CV over RT. Oh, sorry, that's CP dot. I jumped a line, which is equal to V over RT P dot. Right, so m dot I equal to V over R T times P dot. Remember, we were told that that mass flow rate through that valve is experimentally derived as a function of delta P in the problem statement. If it wasn't, what would we have to do here? We would have to do this two ways. You'd have to plug in your mass flow rate for choked and your mass flow rate for unchoked. There. But that's not the case, right? Because we have one truth that we didn't write down. So we'll go back because we know that m dot I was equal to a function of delta P, which seems like it's unhelpful to start with, right? But this just becomes this. And there it is. No fair, Dr. D, you picked the easy one, right? Yes and no. The only thing that makes this harder is if you have to determine choked or unchoked flow, and that's just us plugging in a different equation that we already have, right? That would be the only variation on this. Or, even easier, you're told that it's a low speed flow, so you don't even bother, you just use laminar and turbulent flow, right? You guys have any questions on this one? Do you guys feel comfortable with some of this? Are we starting to get a little bit of this under our belts and feel a little better? Connor, go. Yes. So it is, right? Because remember, they told us that Q, so the way that they have theirs set up, right? They have this defined as, well, as we have this defined as QMI, right? And we were told that QMI is some function of delta P, right? Now, let's play with this for a second. What if this was low speed, right? And we knew that it was laminar. Wouldn't we just have that MI dot was equal to delta P over R sub L? So by them telling us what QMI is experimentally, is equivalent to them giving us our input mass flow rate. For more than likely, you won't be told this, right? And so what will we have to put in there? For a problem like this, you'll either have to be told that it's low speed flow, in which case you'd use laminar and turbulent, so you'd make two models, one for each case, or you'd have to use choked and unchoked, which we also have M dot equations for, right? Question. All right. Yeah, please. So remember what we're trying to do, right? When we make these models, we're trying to fit it into conservation of mass, right? So we want to know what is our mass flow rate through this valve, right? How do we determine this? Well, they told us what it is. It's just experimentally, it's a function of delta P, right? Now, that could be anything, right? Experimentally, this is a function of delta P, right? Or not delta R. Or this is a function of delta P, right? Which were both my laminar and my turbulent flow conditions, right? Or, I mean, if we go back, don't really feel like writing it, but if you go back, right, delta P is also a player in our choked and unchoked flow equations, right? You've got P1 minus P2 somewhere in there. So all of these are a function of it. We just didn't have to pick one. It's okay to leave it as it's experimentally a function of delta P. Because presumably it's something that we don't know about, right? Otherwise they would have just said, oh, it's laminar, or it's turbulent, or it's choked, or it's unchoked. Right?
And was it in the word statement that it's going to be?
Yeah. So if you go back to right, this the pressure difference. Yeah. Sure. So it comes in as that function of, remember, delta, what is delta P, right? So the question was, how do we get this as in terms of PI, right? Remember, delta P equal to PI minus P. So this is just a function of PI minus P over R2 PI. Right? And we can't really do more than that as it is because we're not told what is the function of. Now, again, if you picked laminar, right, and you ran with laminar, that is a function of delta P. Delta P would be PI minus P, and you go with that, right? Same deal with choked and unchoked, right? You would be able to get P1 and P2 from that, or PI and P2. We're leaving it super general though, because you can't just assume what it is from the way that the problem's written. So, any other questions? Yeah, Chris. Mhm. All right, so how did we figure out that M dot CV was CP dot? Good question. I'm gonna go back here. So we have a constant volume tank, right? Because we have a constant volume tank, we can use CP dot is equal to W net, right? Well, W net is just equal, in this case, to WCV because there is no output. Right? So M in is equal to MCV. M dot in is equal to M dot CV. Yeah. Anybody else? Questions? No? We're good? Okay. All right, so let's talk about thermal systems. So with thermal systems, right, remember we define thermal systems as systems where temperature is a dynamic variable and we are typically interested in adding or removing heat from something. As such, instead of using conservation of mass, we're going to use conservation of energy. So in the case of having an open thermal system, right, we've got some boundary that encloses our thermal capacitance. We've got heat energy that can enter and leave due to heat flow, right, due to heat transfer, Q. But we also have heat energy that can enter and leave due to mass transfer. Right? What is that, right? Well, remember from thermo, right? So this is going to be very thermodynamics right now. Because remember from thermodynamics, when you have a fluid enter, it carries with it some enthalpy. And what is enthalpy? Enthalpy is mass times the specific heat times the temperature. Right? So if we were to cut up our fluid into tiny little pieces, right? And we had to push that through a pipe, that's going to require some amount of energy to do so, right? That amount of energy is known as the enthalpy, right? And so we have to take into account the change in enthalpy for this. So what does that look like? Well, if we apply the first law of thermodynamics, expressed as time derivatives, we get the net rate of heat energy stored, well, the rate change of storage with respect to time, and energy with time is equal to the sum of all of my enthalpy in minus the sum of my enthalpy out plus the sum of my heat transfer in minus the sum of my heat transfer out. And this would give me units of watts or power. Okay, so in this case, right, I've got enthalpy coming in top, I've got enthalpy leaving, I've got some heat transfer coming in, I've got some heat transfer leaving. Right? It's all about where we draw our control volume as well. So we need to make sure that we get it. Okay. So yeah, it's just the first law. It's just the first law of thermodynamics, but written as a positive. In general, thermal systems are distributed. What does this mean? Well, in this room right now, we cannot consider the temperature. If it says it's 72 degrees, that doesn't mean that the whole room is actually 72 degrees, right? It's gonna be hotter in some parts, it'll be colder in others. Anything, right? So again, here's another example, right? I have a metal rod and I ask you to hold one end of it. And I'm gonna heat up the end that I'm standing by, right? Eventually, it will get hot by your hand, right? Eventually. Might take a long time, might not, depends on what metal you're holding, right? But eventually, it'll get hot. But the entire temperature of the bar is gonna change according to the length. Right? There's some temperature gradient. Okay? Because we're talking about distributed systems, that means that we need to model everything as PDs instead of ODs. What did I say on day one about doing PDs? Right, I said no, we're not going to do PDs. So what do? We just pretend that they're regular ones and regular D. We just pretend they're ODEs, right? I mean, no, we're going to use it one for one. So we're going to assume that every point on an object, every point within a fluid has the same temperature, but it is an average of the temperature gradient. We're going to be able to characterize thermal systems as two passive elements. Okay. We have resistance and capacitance. Again, we're not going to talk about inertance or inductance for this, right? We have resistance and we have capacitance. Let's talk about them. Thermal resistance. Thermal resistance. Thermal resistance. What element in electrical and mechanical and fluid systems would thermal resistance be equivalent to? Yeah, a resistor, yeah, right? Resistance is going to be resistance in fluids. It's going to be resistor. It's going to be a damper, right? In our case, we've got three types of heat transfer that we're going to cover. Right? We've got conduction, we've got convection, we've got radiation. And if we don't remember those, then I'm going to have a long talk with Dr. Williams and Professor Tan, because that's bare bones minimum what you should have gotten out of that class. So conduction, convection, and radiation. Okay, so for either conduction or convection, we can use this linear model here to talk about the temperature change due to the resistance. It's called Newton's law of cooling. And the heat transfer is equal to 1 over the resistance times delta T. If you rearrange this equation, right, it would look something like that. Does that look like another equation, or maybe two other equations that we have seen previously? Olivia, for the win. Ohm's law. 10 points to Gryffindor. 100%. Looks like Ohm's law, right? It's the resistance element. So these are all building on the same type of field, right? So the change in temperature, the temperature drop, if you will, is equal to the amount of heat transfer times resistance, or Q is equal to 1 over R delta T. Why do we care what Q is, right? Well, for specific applications, we care quite a bit, because Q is going to give us our heating or cooling rate, right? If we're talking about the building. How much heat transfer do I need to make sure that I have the appropriate amount of HVAC, right? So I'm getting rid of the correct amount. As the resistance approaches infinity, we approach a perfect insulator. So the larger, the larger the resistance value, right? The larger R is, the worse we are at transferring heat. So, I mean, think about this. You put in a super large number for R in here, you're going to get a very small percentage of temperature change, right? So your Q is going to be a very small number. For conduction, we define R as X over Ka, where X is the thickness of my material, my segment. K is my thermal conductivity coefficient, and A is the area of the cross-sectional area that I'm dealing with. So K is what? K is a material property, right? For example, copper, right, has a K value that's 18 times greater than stainless steel. So copper is a good conductor and a poor insulator. And so you want to be warm at night, right? Shouldn't put copper in your walls. It's not a good idea. Also, you're just asking for trouble. Really. All right, so conduction, remember, conduction is when two things are touching, right? If heat transfer from things being in contact with one another, that is what conduction is. Convection, on the other hand, is when we have a fluid blowing over a surface, or two fluids passing each other, right? So, our convection resistance is defined as 1 over H times A. Sometimes we see that as lowercase h, which is our convection coefficient. Convection coefficient is derived experimentally, just like many of the other things that we deal with in transport and thermal, right? It's an empirical solution. For example, however, H can be between 50 and 100 times greater than H for air. So air is a much better insulator than water. So again, you don't want to put water in your walls to insulate it, right? And there's other issues that come along with that, but the insulation properties of water are not very good. All right, and then we've got radiation. The heat transfer, Q, equal to beta, Q1 to the 4th minus Q2 to the 4th. It is highly nonlinear, and it's very difficult to ascertain. Beta is the Stefan Boltzmann constant. We're not going to use it in class, but you've seen it. Okay. We're not going to model radiation heat transfer. We good with resistance so far? Everybody doing all right? Remember, most of the time, okay, to leave your resistance as R in your equation. All right, if you don't know if it's heat transfer due to conduction or convection, if you think it might be both, you can leave it as R. That's fine. Okay. Yeah, fine. So the way that we think about it is we want to determine how much energy we need in a system to induce a temperature change, right? So if you have, and yes, to a certain extent, you write it the other way, it's a temperature gradient, right? So you've got a hot temperature outside and a cool one inside, the energy wants to flow into the house, right? How do we determine how much of that temperature change occurs? Right, well, we can figure out what the Q is, right? You can figure out what QH is, right? How much heat transfer you have coming into the house. So it's I would say in practice, it's more of a measure of us determining how much energy we have flowing into a system as opposed to what the actual temperature is. But both of them, it's interchangeable. They go hand in hand, right? We'll see. We'll do a couple today, a couple examples, and they're both very different problems, but you'll see how to handle this stuff all together. All right, thermal capacitance. Thermal capacitance is the measure of a body's ability to store heat due to its mass and its thermal properties. So how much heat energy can something store? That is what our capacitance is. And we actually talked about this, well, not you and I, but we as a whole, right? When we were in thermal. Because there is a measure of this when we talk about this in thermal. It's the mass times the specific, the pressure, sorry, the mass times the constant pressure specific. That is my capacitance. So how much of the material do I have? And how much energy can that material store, right? How much energy can that material store? For example, 1 kilogram of water has more than 4 times the thermal capacitance of 1 kilogram of air. So water can store more energy than air. Another way of thinking about it is it takes more energy to make water do something, right? Okay, so MCP, right? Those are that's it. We've got MCP, and we've got Q is equal to 1 over R times delta T. But we really haven't discussed that much on how to model this, right? We know what the elements are, we understand what they do, but how do we actually put this into practice? And the way that we're going to do that is this, right? So for my lump thermal model, we base it on a heat balance equation, right? Which is essentially the first law of thermodynamics, but we're not incorporating any of our mechanical or electrical work here, right? And so what do we have? And we've got C dt equal to H dot net dt plus Q net dt, where H dot is equal to M dot Cp times T. Okay, so the heat stored in the body is equal to the net heat transfer to the body, right? So okay, this is very much like M dot Cv is equal to M dot in minus M dot out, right? This is just saying that I have some energy that is being stored. I have something that is internal to the system, and that has to equal the amount of energy I have coming in minus the amount of energy I have coming in. Where do we get these sources of energy from, right? Well, we've got C T dot, right? That is, C T dot is our capacitance term. How much energy am I storing in my material? This guy, another way of saying this is sum of H dot in minus the sum of H dot out, Q1 and Q1. So when we are talking about these problems, this is the equation. This is the mathematical truth for thermal problems. Write this one down. Because why? Because certain things happen. What happens if I don't have a capacity? What if I don't care about how much energy is being stored? What if I fully ignore the capacity? CT dot goes to 0. What if I don't have a mass flow rate, in or out? Those terms go away. What if I'm adiabatic? Yeah, admittedly, that's a really lame thermal problem, right? But if we have this equation, right? If we have this equation, we can alter it based on our needs and based on what we know. Right? So let's try one. This is what I call a shell and tube heat exchanger, but what this textbook that I pulled it from calls a double pipe heat exchanger. It's the same type of deal. What do we have, right? Well, we're going to use this to transfer heat from the hot fluid flowing through the tube to the surrounding cold fluid. So T1 is hotter than T2. We're going to assume that T2 is also hotter than the ambient temperature, right? So TA, which is not labeled here, but we should go ahead and assume that there is some ambient temperature surrounding it. Both flows are steady, and therefore the input and output mass flow rates of the tube and shell are m.1 and m.2 respectively. We want to derive the mathematical model for the heat exchanger. So we need a diagram, right? So I'm going to do the diagram two ways. The first one is going to look like this. And I've got m.2 and m.2. Let me just do that. And I've got m.1, m.1. I've got my, did that on purpose, right? The blue one signifies that there's some colder temperature, which we're calling T2. The red one is T1. The diagram also calls out the thermal resistance R1 and the thermal resistance R2. We've got some capacitance in here, C2. We've got some capacitance in here. There's also, because this is important for what we need, we have some heat transfer. Call that Q1. From the hot pipe to the cold fluid. And I've got some heat transfer called Q2 from the cold pipe to the outside. Right? Because remember, I've assumed what? I've assumed that the ambient temperature is less than what the cold fluid is working at. And that'll do it, right? That's a good one. But told you I was going to do this two ways. The other way is I'm going to define my control volumes. I'm going to say that this is my tube. And this is my shell. And I'm going to define this as m.1. Sorry, not to be m.2. Okay. All right, so this is m.2. This is m.2. This is m.1. m.1. I'm going to have Q1 across here. I'm going to have Q2 here. Remember, this wall here has some R2, and this wall in here, these two things are connected. This is R1. Inside, I've got C1, T1, and C2, T2. Either one of these is fine and valid and used, right? What do we do now? So what do we do now? First of all, do you guys have any questions on the diagrams? Yep. Either of these is fine. You choose whichever one works best for your brain. So let's talk input and output here. What's my input to this system and what's my output? So I got the M dot in M dots as my input and the out M dots as my output. That's one option. What else could we do? What was that, Chris? One more time. Sure. So for this particular system, I'm gonna have T1 and T2. I have some hot fluid coming in and I'm getting some temperature out, right? So what is this doing? What is the system doing? We are taking some hot fluid and we're transferring that heat into a colder fluid. And potentially that colder fluid is going to some other process, right? Where it needs to be higher temperature. So we need to know what that final temperature is. We need to know if we're hitting that temperature, right? We can't just leave it to chance. Also, again, fairly simple to measure temperature, right? It's not that hard to measure M dot either, but it's a little bit more invasive to our flow, right? So it's going to disrupt our flow to measure it. Just like Professor Farnsworth says, you know, no fair, you change the outcome by measuring. Anyway. So what are our truths? What do I have? What did I tell you the truth is? If you're going to write down only one truth for this whole thing, what do you want to write down? Yes, Olivia. Thank you. CT dot is equal to the sum of M dot in CP T in minus the sum of M dot out CP T out minus the sum plus the sum of Q in minus the sum. Also, we need to write this one because we have a resistance. All right. So we need to write Newton's law of fluid. That Newton guy, man, is all over everything. Okay. That's all we need to do this. Because what do we have in this, right? If we look back at our diagram, what do we have? I've got a resistance, so I need to know how much heat transfer I have due to that, right? I've got some capacitance in these fluids, right? I've got everything that I need in these two in these two equations. So let's do our reduction, right? We'll start with the tube side. We'll start with tube side. Right, so that was C1 T dot 1. And that's going to equal M dot 1 CP T in 1 minus M dot 1 CP T out 1. So I know it says T1 on the heat exchanger, right? I know it says T1, but because of the way that this is going to operate, the temperature entering and the temperature exiting that heat exchanger have to be different, right? I'm exchanging heat. I'm losing temperature to the hot fluid with the hot fluid, and I'm gaining temperature in the cold fluid. So we can't just say that T in is T1 and T out is T1, because otherwise this whole part of the equation is zero. So, no, because remember, it's the same M dot. It's a single inlet, single outlet. Good question. The question was, are the M dots supposed to stay in and out? And they're not, because it's one inlet, one outlet for each of our tube and shell. All right, so I know it's not explicitly stated anywhere that T in will be different than T out. But if they are in fact the same, this whole part of the model goes to zero. And we haven't exchanged any heat, which is problematic. Well, I guess not true. We wouldn't technically not have exchanged any heat. It just means that we've exchanged such a small amount that it didn't change the temperature. Right. But anyway, what do I have, right? Plus Q in. Let's go back, going back here. Remember, we're doing the tube. For the tube, for the central pipe, do I have any heat transfer entering that pipe? Do I have any heat transfer entering that pipe? No, right? That's where our heat transfer is generating from, right? It's starting from there because it's the hottest thing. So we have no heat transfer in. How much do I have leaving? And how much do I have leaving? Q1. Exactly. So plus 0 in minus Q1 in. So we can add some things in here, right? We can make this. Instead of minus Q1, let's make that thermal resistance 1, T1 minus T2, right? Because that's just 1 over our delta T. So I've got this, right? And we can rewrite this. Was that? Okay, yeah. So where did I get 0 minus Q1? Remember, this is the sum of my Q in, and this is the sum of my Q out. So if we're looking just at the central tube, I have no heat transfer coming in. I only have heat transfer leaving, which was Q1. And we can rewrite Q1 in terms of Newton's law of cooling, right? So I've got everything here in terms of T1 and T2, right? I'm going to algebra a little. And that's that. So essentially, we take our conservation of energy we look at each part of our system and we see this is what I have coming in, this is what I have leaving, right? We put it in there. We basically plug and chug is what we have. So we're going to do the same thing on the tube side, or the shell side, sorry. Shell side. Yeah, Chris. Yeah. So, okay. So, remember, the inlet and the outlet have their own temperatures, but the average temperature inside is still T1 and T2, right? We're still lumping those. But you can't ignore the fact that the inlet and the exit are going to have different temperatures. Otherwise, there's no reason to do this problem because this just goes to zero.
So now we're going to do C2 and C2.
Yep. So now we can move to the shell. And so we have C2 T dot 2, and that's going to equal what? Well, we've got M dot 2 CP, I guess technically be CP2 T2 in minus M dot 2 CP2 T2 out plus how much heat transfer do I have coming in? Yeah, my Q1. Yep. Q1 minus Q2. All right. We'll make some substitutions. We'll do some simplification as we go. We get this. We can algebra. Does it matter which side you put the ambient temperature on? No. Constant. Doesn't matter. Whichever side you want. Okay.
And just to clarify, the two T's, the T1, T2 are the difference of T in and T out, right?
Yes. Yes. So the question was the temperature gradient associated with the heat transfer portion, right? You need the temperature in minus the temperature out, right? So the temperature on the left side of the Q minus the temperature that you have on the output side, the right side. Okay. All right. You guys have any questions on this one? No? Feel okay with this? Too soon to tell? Huh? What's it?
A lot of it reminds me of Turtle, how you get in place and fall off. And start plugging stuff in.
Yeah. Indeed. All right. Well, I've got one more. And this one's a little bit different. Little bit. So I've got a wall here. It's made up of brick, fiberglass, and sheetrock. There's some temperature outside. I've got some convection heat transfer coefficient on the outside and the inside. And I know what my conduction coefficients are. We'll do this assuming that there is a capacitance for each section of wall, meaning that the wall is going to actually absorb a certain amount of energy, right, before, right, so it's going to absorb, each one's going to store some energy in it. So how are we going to do that? So this is, I'm fairly confident that you guys have seen resistance modeling of walls in transport. I'm fairly confident that you've seen it. It's a very common technique. So what do? We got to draw our picture, right? What do I have? I've got this wall. It's got 3 sections. Here's my outside temperature. Here's my inside temperature. I've got some brick. I've got some fiberglass, and I've got some sheet rock. I'm going to assume that my heat transfer goes from the outside to the inside. So I'm assuming that this, right? I'm assuming that T out is greater than T in. Okay. I can also draw this in a different way. That will make it look like a circuit, right? Remember, there was some H air here, some H air there. That's important, right? Why? Because that lets us know that there's convection that we have to model on the outer surfaces of the wall. So if I wanted to draw this as a circuit relationship, right, I would start with T outside. Then I'm going to have to go through R sub H, right? I have some convective resistance that I'm going through. Then I'm going to hit the wall, right? And once I hit the wall, I'm going to go through half, not R over B, half of my brick resistance. And then I get to the middle. And the middle is where I'm going to say that the temperature of the wall, the temperature of the brick is T sub B. And this is storing some energy, C sub B. So I have a capacitance, right? Coming out, I've got RB over 2 directly into R sub F over 2. That's going to get to the middle of the wall, middle of the fiberglass. I have a capacitance. I think you guys pick it up, right? That's RH. And it's really this. So I can create this as a circuit model, right? So why is that the resistance over 2, right? Well, because it's half the distance. Remember what the conduction resistance is determined by the length that we're traveling through, right? So it's literally half the total resistance. What if we didn't have capacitances here? Right? What if I said, you know what? We're just going to ignore capacitance. What would we have? Well, you would just have something that looks like that. We'll do that there. You can't call them TB. You have to call them T1, T2, T3, T2. Because now you have to track the temperature at each of the junctions. Right? You need the surface temperature of the wall, and the temperature between the brick and the fiberglass, and the temperature between the fiberglass and the sheetrock, and the temperature between the sheetrock and the surface wall. So there's quite a bit more. But this has its advantages, right? Because now it's one straight shot here, right? Because Q is still in that direction. We're going to do this the capacitance here, though, because it's a much more real world model, right? Much more real world. I don't want to say this. Much more real world because real world materials store energy, right? Things store heat. Things store heat. All right, so what do we do here? Right, I've got my diagram. First of all, is everybody okay with the diagram? You guys see where it came from? Do we get the concept behind this diagram? Have we seen this before? So.
With the TV, so if you're taking that in the middle of the, so that's why it's the
Yeah, so the question is the reason that the temperatures, the resistances are halved, is that 100%. When we do a model like this and we're lumping it all together, we assume that everything is a single temperature in the center of the wall, in the center of that section of wall. All right. Yeah, Chris.
Why are we considering the resistivity of the air?
Because there's some convection heat transfer that's going on there. And so we need to, so basically, if we go back here, big giveaway is because in the diagram, it was given to us that we have H sub air, and we were given a value for it. Again, is there always heat transfer, convection heat transfer going on in a house at all times? No. Right? The wind isn't constantly blowing all the time, right? I'm sure. I mean, this is a very specific thing, right? But you want to run a model like this both ways, because in the off chance that the wind is blowing, which is, I know, crazy talk, right? But if the wind does blow, we want to know how that affects our heat transfer. Problem like this is mostly we're trying to understand how much heat is getting shifted into the home, so we know what the maximum cooling load is, right? We want to know, okay, well, I am inputting, 100 joules of heat transfer into this house. I need to size appropriate. I need to size an appropriate cooling load based on how much I want to cool it, right? So another way of thinking about this is, if it is in fact, 120 degrees outside and you want your home to be 70 degrees, how much energy do you need to make that happen, right? That's what we're, because that's going to size how big of an HVAC unit that you potentially need. Okay. So what do we do here? Apparently my voice got deeper. Let's try. Hold on, please hold. Please hold. Is that better? Worse? Is it worse? Is it high pitch now? Thank you. Too bad. I was hoping it'd be high pitched. Anyway, what are my inputs and outputs for this? What's driving this system? What am I interested in getting? Right? My input is my external temperature, and my output is my internal temperature. Why? Well, I want to know how the output's simple, right? I want to know how cold I can get the inside to be, right? Or hot, whatever you want to do. The thing that's, remember, we're not running an HVAC in this. We're just trying to determine the amount of heat transfer that happens based off of the capacitances that we have and the external temperature driving this because it's higher than the internal. What about mathematical truths, right? Well, Dr. D, you said that as long as I had this mathematical truth, you said as long as this one was there, that's all I needed. So I'm going to go with that. Yeah. All right, but we also want this one. Remember, we've got resistors. Okay. Do we have any mass flow into or out of this system? So we have no enthalpy. Those both go away. If those go away, what am I left with? Yep. So where do I put all this, right? Where do I? Good.
Evaluate it at each point. So how we look at like T1, T2, T3, T4.
Yep. Sean is correct. What we are going to do is we're going to look back at our circuit diagram, right? And essentially, we're going to use KCL at each of these nodes. I know how much heat transfer I have. Let's call it this, right? Let's highlight these right here, and right there. I know how much heat transfer I have going into the red dot and how much I have leaving the red dot. I know how much I have going into the blue dot and leaving the blue dot and the green dot, right? So I should be able to write one equation for each of those. And look, I've got a nice capacitance here as well. Another way of thinking about this is, right? If you don't like to think about it as KCL, this is conservation of energy, right? We just wrote the equation. CT dot is equal to the sum of my Q coming in minus the sum of my Q leaving, right? So what's happening here? I put some heat transfer in, some of it gets stored in my capacitance and some of it leaves, right? So let's start it up with that red one. Oh.
So would you want us to write the KCL equation with the truth still, or just go straight to reduction?
You don't need to write the KCLs down. You can just do the reduction from there because we wrote down the big dog equation here. This is the equation that we are going to evaluate at every single one of those nodes, right? That one. And we're going to substitute in this for Q. Those two equations are all that we need to do this model. So what do we do, right? Well, let's start with the red one. So I didn't name it properly. Well, what do I have? Well, let's go back and look. What do I have here? What's my Q in? Well, that's just gonna, those two resistors, they're in series, right? Can't I combine these? Call that R1, R2, R3, How do we combine resistors in series? Just add them. Just add them. So I'm going to write those as R1, R2, R3, and R4 because I don't want to rewrite RH plus RB over 2. Right? So what do I have coming in to the red node? Well, I've got the heat transfer due to me crossing these resistors, which is going to be 1 over R delta T. Well, that's going to be TB minus, or sorry, T out minus TB, right? What do I have coming out? Well, I've got 1 over R2 times TB minus TF, and I've got CT dot coming in, or being that's staying. So 1 over R1, T out minus TB. C1, or let's call it CB TB dot is equal to that. That's my heat transfer coming in. Subtract my heat transfer leaving. TB minus TF. We can algebra a little bit. And that would be fun. What about the fiberglass? Remember, these are linked, right? So the output heat transfer from the brick is the input to the fiberglass, right? So I have that. What's my output heat transfer? Yep. 1 over R3 TF minus TS. Remember, you want one equation for every energy stored. Now we have one more. We'll do this one more time for our the next equation, for the blue one. Perfect. For the blue node, I've got my sheetrock. I'll make sure I write this down right. Right, remember, it's going to be the output from the other one. 1 over R3 TF minus TS. And what do I have leaving? Well, I've got 1 over R4 TS minus T in. And now I've chained everything all the way down the line, right? Each one of these is in terms of the other, right? These are all coupled together. And because of that, And if you really wanted to, you could chain this all the way back, right? You could solve this one for TF, plug that in to the TF equation, right? Then solve that one for TV, plug that into the TV equation, and you'd have something that is T out in terms of TI, right? And you'd be able to tell me how the temperature, the output temperature affects the input temperature, right? Or it's a bad way to put it. The outside temperature affects the inside temperature, right? That's how you'd be able to do it. What if the heat transfer was going in the opposite direction? What if it was hotter inside than it was outside? I know, nobody's used to that in these parts. Yeah, all your signs would flip. That's it. All your signs would flip. You guys have any questions on this?
Will you ever ask us to chain all those together, or did you?
Not for now. We're getting there. We are hurtling towards that point very quickly. Right. So the question was, will I ever ask you to chain them together? Not on an exam. Once we get to Laplace transforms, there is utility in it, but you'll see when we get to state space, you want them in as systems of first order differential equations. It's going to make life a lot easier. All right. You guys have any other questions on these problems? These are really the two flavors of the heat transfer type problems that we have, right? The thermal problems. You've got heat exchangers, right? And you've got basically resistance type problems. The homework has both kinds. Homework has both. All right. If nobody has any questions about anything else, you can ask me a question about anything otherwise that you want. Blake.
The exam cover material all the way up until today.
So right then, till that last sentence. The exam does cover everything till that last sentence I just said, not including this sentence. Mark it in your notebook. Anything else?
You might have already said it, but do Thursday students go into class on Thursday?
You don't need to come into class on Thursday. If you are scheduled to come in, you can take it from your wherever you would like to. If you are a commuter student and you're going to be on campus and you don't have enough time to get someplace to take it, I'll be in the room anyway. Then you guys can come in here and take it. Don't, obviously the highest number of people that can be in this room is 12. So, you know, if you don't need to be here, please don't be here. Connor.
So I think Don asked this earlier, and I think you said it's in Discord.
Yeah, but I think I typed it in.
Did you send? I don't know.
What we typed in Discord for the question?
Yeah, hold on, I'll tell you. If you have that question about the number of exam questions, type exclamation, how many questions into the Discord.
Exclamation, how many questions?
Yes.
Okay, I kind of have a similar question. I was going to ask, are your exams mostly or is it all written in the exam?
Wait, Connor, say that one more time. Sorry, I didn't hear you.
Are your exams, I don't know, I've been there before. Is it going to be all arithmetic or are there going to be some like?
So how the question has to do with the exam format. It's based very much on how the homeworks are structured. So there's going to be short answer section with theory stuff, and then there's going to be some problems that you have to do. Okay. All right. Anybody else? Anything else? Just so you guys know, since some of you have had quizzes with me before and some of you have not, at the beginning, there are festivities at the beginning, and then we will get into the exam. So show up on time. That is all taken into account. You'll still get 2.5 hours to work the exam and 30 minutes to submit. So don't worry about that. But we probably won't start for about 5 minutes beforehand, right? So, yeah. That's not a weird question. Somebody asked that earlier. I don't need to watch you guys submit it. That's fine. Once you're done with the test, you can log off of Zoom and do your thing, take pictures, scan it, whatever it is. Okay. Sean. I would prefer either Word or PDF, one of those two. It works best with LoudCloud. Otherwise, LoudCloud gets mucked up. All right. If nobody else has anything, I'll leave that up there. I have office hours from 3 to 5 today and tomorrow. You guys need me. Take it easy.